let you ask questions. So Krishna has gone through the last lecture, and I've seen his lecture. It's pretty well done, but it's also pretty fast-paced. So after you have a chance to look at the material, after you have a chance to kind of think about it, you may have questions. So I want to offer that first, going through slide by slide, allowing you to ask questions before covering new materials, okay? And if there's no question at all, we can go through sort of new materials, okay? We don't have a whole lot of materials left, so we can kind of take it, go slow, and make sure you understand all the important thing. Okay, so the topic last time is multi-stage amplifiers, and each stage basically consisting of one main transistor. And you'll see many transistors, but really for each stage, one transistor is doing all the work. All other transistors facilitate to bias that transistor in the desired state, okay? And so there are three configurations. There are common source, there are common drain, and common gate, okay? And these characteristics are sort of summarized here for you as a convenience. I wouldn't say you need to memorize this, but it's good to have intuitive feel. So when you see the circuit, it's sort of your second nature to think about, oh, it's high impedance, high input impedance, low output impedance. It's primarily current drive, voltage drive, and so on. So this is helpful, and when you start to put them together, you can sort of understand the functionality a lot easier. Yep.
Can you confirm for the common source?
Yeah.
The output resistance, is it RS or because Krishna changed it in the middle of the lecture?
So it should be RS. I don't know what's originally in here. So this should be RS, and it is RS here. These symbols may have some leftovers from a bipolar notation, in which case it may be written as RE emitter. So I can, actually there is kind of an intuitive way of looking at it. So let's see, let me add a page here. Okay. So this kind of universal way of looking at this. So this is kind of primarily for your intuition, okay? This is not a golden rule, you have to memorize it, but there's kind of a universal way, universal treatment of different transistor configurations. So let's, for example, looking at MOS here. So MOS, let's look at NMOS. It doesn't matter what it is. So normally this is a transistor, right? And for the sake of this AC treatment, I'm going to ground every terminal as a starting point, okay? And I'm going to add a resistor at every node, okay? So obviously this is not a circuit. You cannot have every terminal grounded. There's nothing to do, okay? And so I'll have RG here. I'll have RS here. I'll have RD here, okay? And you can think of this as a universal configuration in what way? Well, in a common source, common source, basically we are going input from the gate, output from the drain. So this is really common source here, right? And common gate input is here, right? Output is at the drain. So this is a common gate configuration. And we have a source follower or common drain. Common drain will be going from here. So this is kind of a common drain configuration. So you see, well, in principle, 3-terminal devices, if you do random permutation, there are 6 possible permutations. But there are really only 3 useful ones. So these are the 3 useful ones. It's not in arbitrary pair. So gate driving output to the source is useful. Gate driving to the drain is useful, or source driving taking output from the drain is useful. Okay, question? No? Okay, all fine. So the next thing is, well, obviously there are gain associated with that, and you have analyzed the gain, okay? And we don't, the gain is kind of also very generic, that you can kind of more or less kind of have it kind of in the back of your mind, you know. For CS, this will be gain, primarily voltage gain, and that will be minus GM R0, okay. R0 is for the intrinsic semiconductor, okay. If you do a small signal analysis without external resistor, that's intrinsic gain you got. So this is kind of a intrinsic semiconductor. For a common drain, common drain, source follower, these are almost 1, right? And for common gate, its AV is same but positive. It's GM R0, but this is also basically a current buffer, and current gain is minus 1. The minus just accounts for the direction. Okay, so it's kind of a very simple way of looking at it. Now, even more useful way is to look at the input impedances. Okay, here we don't distinguish input and output. There are 3 terminals. So let's say any one of them could be used as input, or any one of them could be used as output. So I ask the question, if I look at gate, I would temporarily kind of cut here, and I'll look into the impedance. So I'll call this RG here, okay? So it's, I don't know if it will be input or output, so it's just a terminal impedance, okay? So RG, looking into gate, for MOS, gate is insulating, so it's always infinity, okay? So that's a nice, easy part. Not too long ago, 5 years ago, we covered both bipolar transistor and MOS. Bipolar has a finite input resistance, so this becomes more complicated. So for MOS, luckily, it's simpler, infinity, insulating. That's good, okay? Now let's look at, now if I'm looking at drain, so I'm kind of cutting it here temporarily, right? So when I look at the impedance, I look basically in here. I'll call this, I'm running out of symbols. RD, I call this RD. The outside, RD external. Okay, let me distinguish it here. RD, these are external, and this RS external. Okay, just to distinguish it. Okay, so now I'm looking into the RD. Okay, RD, we have done a few times small signal analysis. If you like, we can do it again, but this is basically common source with degeneration. So you not only see the output resistance of the transistor, which is small r0, but when there are this external resistor attached to the source. This is basically GM R0. So this is a dimensionless number. It's just the gain. This external RS is being boosted up. Okay. So when you look down into a drain, when there's something hanging on the source, you see a very large resistance. Now, for completeness, we should add R0 here, right? So in case there's no source degeneration, RS external is equal to 0, then in this case, when you look down from the drain, you see the output resistance of the transistor itself. Okay? So that's kind of an intuition. Let's complete the cycle. So that's a very compact here. What do I do? So again, I cut it here. When I look into the source, so I have RS here. To remember, this is not the RS. Maybe I should change the symbol to small r. Let me change the symbol to small r, so there's no confusion with the external one. So I'll call this RG, I'll call this RD, I'll call this RS, okay? And I'll change these symbols also. So RG, RD, okay, and RS now, okay? So RS, when you look into the source, again, we obtain this from hybrid pi model. We do the full small scale analysis. You look into that, its dominant term is 1 over GM, okay? 1 over GM. So the totem pole of all these different magnitudes, when you think of all these different parameters, well, R0 is a big number, so a big number. So R0 is a big number. And it's much bigger than 1 over GM. Whenever you are comparing these two terms, the output resistance of a transistor, small r0, is a big number. It's usually like hundreds of kilo ohm. And 1 over GM is usually a few kilo ohm. So it's like tens of times to 100 times larger. And whenever you encounter this amplified one, if you have a GM R something, RS external, times R0, I'm running out of room. Let me erase this. So the largest number is this amplified one, GM RS external, okay, times R0. This is going to be much larger than R0. This is going to be much larger than 1 over GM. So these are the three orders of magnitude. And as we go through examples of multi-stage amplifiers, sometimes we want a low impedance node. We'll go through that example again. And you know what stages to use, what stage makes sense to use in a particular place. So this is a universal way of looking at things. And we can kind of, these are very simple, right? So mentally, you put that in the back of your mind. When I'm learning this, I have a piece of paper actually just on this that I carry with me until I sort of remember. Then I go back and just look at this standard configuration, okay? So common source with degeneration, so with RS here, that's the gain. So, gain GMRL over this. And input resistance, you are looking into the gate. So maybe it's easier if I just draw this, right? So input resistance, you're looking into this. So that's infinity, so check, okay. Output resistance, you'll be looking down from the drain. So it's R0 plus GMRS. So check, this is consistent with our universal model, right? And if we look at common drain, so common drain is like this. And input, again, input, that's infinity, check. Output will be looking into the source, that's 1 over GM, so check. And gain is, well, almost like common drain with source. So gain you can always analyze. Input output is kind of, it's useful if you have an intuitive feel. Common gate, so common gate is the case where we go input here. So this is Ri, common gate, right? And this is R out here. Ri, you look into that, that's 1 over GM, check. Ro, you look into this, well, if I have a bias here, so I have a bias here, I have R, I forgot to correct this, I have RE here, I call this RE, and so this, it's better to be called RS here, so RS. So this is R0 plus GM R0 times RS, so check. So basically, the input-output resistance all follow these very simple universal treatment. Okay. At least for the next month or so until final exam, this will be a very helpful thing for you to do all your homework, analyze lab, and so on. Okay, useful to remember that. This is putting that analytical expression into perspective. How big are they? Common source with degeneration. Any questions here? I don't meant to repeat the lecture. I meant to really answer your question. Okay, so let's take a look at the examples. RO, so when it is very large means it's something like a GM R0 and either another R0 or RS or something. That's very large. When it is large, it's on the order of R0 when it's large. When it's small, it's like something like 1 over GM, that's we call small, okay? And common gate large, that's on the order of R0. And gain for moderate, we meant it's like a GM R0, that's moderate. Small usually it's like GM R0, but usually there is that factor here, such as this one. So GMRL times 1 plus, okay, so this is like GMR0 and 1 plus GMRS. So that's what we call small. And 1, well, is 1. Okay, so it's kind of how to interpret this table here. Okay, how to interpret the frequency number? Small because there's a Miller effect. So you all learn Miller effect. There's a Miller capacitance. That's why the bandwidth for common source is small. Okay. And common drain, it's large. It's large because there's no Miller effect, and the input impedance, the impedance of the node, of the important node, is small. So this is because of there's no Miller effect. Okay, no Miller. And the impedance, usually the high Z node. So this impedance in that node associated with a big capacitor, the impedance is small. So the RC time will be small. So that's what we meant by large. Okay, and moderate will be something in between. Okay. Okay. Any questions? All right. So single stage, we cannot meet all the requirements. Okay, that's pretty straightforward, and therefore we use multi-stage. Multi-stage, we have input stage to take care of the input impedance, output stage to take care of the output impedance. In the middle, we need more than one stage to give us sufficient gain. The modern transistor getting smaller and smaller, and the amount of gain we can get out of it is also getting smaller. So we need multiple transistor stages. And sometimes we also do that for, so not just gain, sometimes we do that for bandwidth. A particular node that has a big capacitance, well, sometimes there's nothing we can do about that big capacitance. We can, if it is Miller effect, we can cap the gain, or if it is high impedance, we can transition to a low impedance. So that's all the trick we can play with multi-stage amplifier. Okay. DC coupling. So we really learned two ways of biasing circuit. Let me add a page for comments here. So biasing, there are really two ways of doing biasing that we have learned in this class. One is more like a discrete technique where you physically set up a bias. You physically set up a bias with resistors. Okay, so for example, for a common source, you set up a resistor and resistor divider that generate the bias for the gate. And in order to insulate that DC voltage from your input, then you have a coupling capacitor. And for the output, you have a coupling capacitor because this may be feeding to the next stage. So, let's say we have two common source stage, right? And this second common source stage, it also needs bias. And we have another resistor pair to bias it. So this DC point may be different from this DC point. And we use a capacitor. We basically use a capacitor to separate these two DC values. So we don't worry about the left side of the DC, right side of the DC, if they don't match, or if my output swing changes, the output swing is changing the bias of the following stage. That's obviously not desirable. So a capacitance fulfill that job. These capacitance are relatively large. So in the integrated circuit where everything is integrated, it's not so convenient to have. So for integrated circuit, we use basically DC biasing. So biasing design here could be really interesting. So for common source, for example, we really do current source biasing. Okay, and that's a preferred way of biasing the circuit here. And how do we generate these biasing? Well, there are current mirrors. So here, you could have PMOS, and that set up this transistor here, and this could be a current mirror that Okay, we're back. So, you know, we do current source, and here we have a reference here, okay, I reference. So this kind of, we set up the bias this way, and now going from stage to stage, it's really interesting how we set up the DC bias when we go from one stage to another, okay. But this is integrated circuit biasing, okay. All right, so let's get back to here. Impedance match. These are the general rules. I think it's easier to look at examples. Okay. So the first example we talked about is two common source stage to boost up the gain. So one common source has a gain of GMR0. If you put two stages together, the gain multiplied, so you get a higher gain. You also have many other disadvantages. Okay, so this is a specific example of a two common source amplifier. So first common source, and you feed it to the second transistor, also common source. You go from output here to the input of the common source. Okay. Any questions on this circuit? What are the disadvantages of this circuit? Do you remember intuitively? So you do get higher gain. You multiply the gain. Yep.
You need double the power.
Double power, but you unfortunately cannot escape that. So high gain, you do, yes, power consumption is always a parameter that is always a constraint. So no free lunch. But we probably cannot get away with that. What are the undesirable things here? Bandwidth, yes, bandwidth is a problem. So if we look at kind of ideal biasing, so you know we have current source biasing here. And so here is input, and this goes to another stage, and assuming we have another current source to bias it, okay. And the Miller effect is indeed a problem here. So there's a Miller effect here from input to output. So Miller capacitance from input to output. And this has a high gain, and it's an inverting gain. So there is a Miller effect here. And the second stage is identical, so it doesn't help. It doesn't hurt more. It's the same bandwidth, but both stages are low bandwidth. These are low bandwidth stage. So that's the disadvantage. Yeah?
For an amplifier, if it has positive gain, is it possible that the 1 minus A, if A is like greater than 1, is it possible that
negative capacitance? It is possible in the circuit to create something that behaves like a negative capacitance. And you know what is a negative capacitance in circuit sense? It's an inductor, so 1 over j omega c, and c become negative, so it becomes j times a positive number. So it is an inductor, and there are some circuit tricks to synthesize a block of circuits that looks like an inductor instead of a real inductor. It is possible. You usually work for some limited frequency range. Okay, so that's two common sources. This is more an exercise. There are a few classical combinations of multi-stage amplifiers. Common source usually is not one of them. People do use them when you need gain, but it's not the most creative circuits people will do. Okay, circuit is in a way a creative art. It's sort of becoming mature. You know, a lot of very clever circuits. You look at it and say, how do people come up with that? I wish I had come up with that. So over the years, there are many of these collections that people know now. So if you want to study to become an expert circuit designer, you will look at all these kind of examples. This is like a chess master. You know, you have all the classical sets memorized. So this is not a particular elegant design because of the bandwidth problem. Okay. So there are various ways to extend the bandwidth, but achieve the same amount of gain, right? So one of the trick is to insert these common drain stages here. Here we still maintain. So this is a three-stage structure. You know, we have common source. Sometimes it's easier to put back the transistors rather than looking at the full scale transistors. And we follow by a common drain, okay. Common drain. So this will be a source follower, okay. So the current biasing is here, and okay, and output from here, it goes to another common source stage. So, you know, it's sometimes easier to just restore this. And let's see whether this solve the problem or not. This transistor has this has a Miller capacitance here, okay, but the input resistance can be very small. So the Miller here, RC, C is large, so this stage has a big C, but if you make sure your RS or Rin is small, RS is small, then it's not a big problem, okay. The second stage here, you have CGS here, this is CGD, gate to drain, gate to source, but the voltage AV is 1 here, so the Miller effect is no problem here. Now going to the third stage, we go back to CGD again, and we have a moderate gain. So when we take output from here, we again have a Miller effect, right? So again, we have a Miller effect we have to worry about here. But now the impedance, we have altered the impedance. The impedance, you are now looking into the source. So the impedance that this large Miller capacitance sees is now 1 over GM. So these are, again, from that universal treatment. Looking into the source, you see 1 over GM. So you lower the impedance. You did not do anything to the capacitance, but you lower the impedance. RC still become smaller, okay. Versus a pure common source stage versus the previous cascaded common source stage, okay. So let's compare them here. So this is a CS plus a CS without source follower in between. And indeed, you have Miller capacitance here, right? So that's a problem. This is a Miller problem. And you look into the resistance. Okay, you look to the right, it's infinity. So it's only coming from the previous stage. You look into the previous stage. You look into the drain. When you see the drain, what do you see? Which impedance do you see? R0. So you see R0. So here we go from R0 to 1 over GM. So we cut resistance down by about a factor of 100. And so your bandwidth now, it doesn't become the bottleneck. The next guy will become the bottleneck. Okay. Yep.
So for the CS plus CS, so you also look into the source, right? So the impedance should also be 1 over GM, right?
So this is the big capacitance node, right? The Miller capacitance is at this node.
Oh, I see.
Right? So you look at the node with big capacitance. Okay, all right. So, and well, these are kind of example. In this case, we're solving another problem. In many cases, we have to drive a large load capacitance. Okay, this is not Miller capacitance. This is load capacitance. In some, ultimately, your circuit need to drive something in the physical world. So you don't get a chance to choose the impedance of a load that you drive. So it's unavoidable. So in that case, you have to design your circuit, right? So your output stage, you need to design your circuit so that when you look into this large capacitance node, you don't have high impedance. And if you just have a common source, you look into that, well, we look up, you see RD. You look down, these are AC short. This RS is AC short, so you don't see that because of shunting capacitance here. So you see drain, you see R0. So you look down, you see R0. R0 is big. R0-CL combination, not good. Bandwidth limiting, right? So what do we do? Well, we do the same trick. You add a source follower. So here is CS. This is just a small signal circuit. Okay. And so what do? We add the source follower. So now you are looking into the source. So now you change the impedance from R0 to 1 over GM. And that solves the problem. Okay. All right. Any questions? So these are sort of the bandwidth extension examples. And this particular combination is classic. It's called cascode. Cascode, you have to, at least at the end of this class, you should know the difference between cascade and cascode. Multi-stage amplifier, you cascaded many stages, so cascade, okay. Cascode come from terminology in vacuum tubes. So it is a known topology in vacuum tubes. And when transistors are invented, people use the same terminology. If you look up in the dictionary, there's no cascode. There's no word called cascode, okay? But the vacuum tube designer in the 40s, 50s, they know what is cascode. So we just use the same terminology. Cascode is common source followed by a common gate. And this has many advantages. It's a classic stage you'll see everywhere. If you look up circuits, you can find this block, there's a cascode here, there's a cascode there, you find it everywhere. Okay, like current mirrors, you find it everywhere. So this is a good stage, right? And this stage solves the Miller capacitance in a different way. It's kind of in a different way. So Miller capacitance is still here. CGD is still here. The second stage, well, we normally don't consider source and drain has a big capacitance. So the second stage does not have a big Miller capacitance. But the first stage could have a big Miller capacitance, the CGD here. For this class, we kind of simplify to consider only CGD and the CGS. So We kind of focus on these two. These are the dominant effect. There are many other smaller capacitance. We just ignore them, okay? So CGD, the problem solution here is we limit the gain of the first stage, okay? So I'm applying now the looking method, okay? You can solve this small signal. I think that's what you did in the lecture. So let me try this looking method intuition here, okay? So the first stage is a common source stage, right? And common source stage, you know the gain AV1 is minus GM1. We need to keep track of GM. Whose GM is that? So GM of transistor 1, GM1 times the total output R out, okay? And what is R out? R out is here. You look down. What do you see? R0. And then you look up. You see 1 over GM. So R out here is minus GM1. It is R0 in parallel with 1 over GM2. So 1 over GM2 here. And we say R out, RO is much bigger than GM, even though it's a different transistor. It's still much bigger. So this is basically, just by looking, you can say this is minus GM1 times 1 over GM2. So GM divided by GM, it becomes dimensionless number. And two transistors, they don't necessarily need to have the same GM. Remember, GM is related to the size of the transistor, W over L. So if these two transistors doesn't have the same W over L, even though they do have the same current, they are biased in the same vertical chain, they have the same current. GM could be slightly different, but for the sake, we say, well, they are comparable. So the gain here is minus 1. So as a result, the Miller capacitance, so now Miller Cm for M1 is now equal to, Cm is now equal to 1 minus AV times CGD, and AV is now minus 1, so it becomes 2 CGD, right? You kept the gain. You kept the gain, so you reduce the Miller capacitance. It's twice bigger, but instead of 100 times bigger, twice bigger is tolerable. Okay. Now, the ingenious design of cascading these two stages